Assalamu alaikum viewers, I am Muhammad Ibrahim on the platform of Dimensional Physics. Viewers, आज मैं आपके साथ अपना एमफिल का जो वाइवा है मॉक प्रेजेंटेशन वो शेयर करूंगा। तो आइए व्यूअर्स स्टार्ट करते हैं। बिस्मिल्लाहिर्रहमानिर्रहीम। Assalamu alaikum, I am Muhammad Ibrahim and my research topic is preparation and characterization of doped polyaniline manganese dioxide composites for seaback measurements. I will provide an overview of my research including objective, synthesis, methodology, result and discussion. I will also discuss the implementation of my research and its potential application. Thank you for joining me today and I look forward to share my research with you. So these are the contents of my research work. As you can see that introduction to polymer, conducting polymer, manganese dioxide, polyaniline manganese dioxide composites application, seaback effect, objective of my research, synthesis of polyaniline doped with SCl, synthesis of polyaniline MnO2 composites doped with SCl, results and discussion, X-ray diffraction, DC conductivity measurements, seaback coefficient measurements and conclusion. So you can see that next slide is introduction to polymer. The word polymer is the combination of two words poly and mer. Poly mean many while mers mean parts. So polymers are called macromolecules and they are huge molecule due to their complicated shape. Polymers are the lengthy covalently connected chain of atom as a building frame, and these building frames are called monomers. By repetition of monomers, these polymers are formed by the process of polymerization. So you can see these is the monomer, and by repetition of this monomer you get polymer. Here conducting polymer. Conducting polymer are the organic polymer having semiconducting structure with conductivities that is equivalent those of semiconductor. For example, polyaniline, polypyrrole, etc. These are the potential applications of conducting polymer, including electrochemical sensing, energy storage devices like supercapacitor, fuel cells, shielding against electromagnetic field and light emitted diodes. Polyaniline. In 1862, Henry Lithpe gave polyaniline by polymerization of aniline black. Polyaniline is a semi-flexible rod polymer, is a conducting polymer as well as organic semiconductor, and by repetition of aniline we get polyaniline. So you can see that a benzene ring is connected with NH bond. And this is the structure formula of polyaniline. Applications of polyaniline in biosensors, electrochemical batteries, electromagnetic shielding. Manganese dioxide. Manganese dioxide is the black brown solid that occur naturally with formula MnO2. MnO2 is an inorganic molecule. In manganese, both anions and cations are octahedral coordinate. It means it has square bipyramidal type structure. Each of the manganese atom is surrounded by 6 of the oxygen atoms, as you can see that. And these are the applications of manganese dioxide: rechargeable battery packs, ceramic materials, oil and paints, etc. Applications of polyaniline MnO2 composites. Polyaniline manganese dioxide composite interesting due to the following properties like photovoltaic panel, electromagnetic interference shielding, supercapacitor, biosensor and electrochromic display. Seaback effect or thermoelectric effect. In 1821, Thomas Seaback discovered thermoelectric phenomena called Seaback effect. The Seaback effect occurs when the temperature gradient of dissimilar semiconductor causes an electric potential between them. The Seaback coefficient is calculated as the ratio of potential difference to temperature difference. S is equal to delta V over delta T. The unit of Seaback coefficient is millivolt per Kelvin or microvolt per Kelvin. The Seaback coefficient is a -4 n-type semiconductor while it is positive for p-type semiconductor. Seebeck effect play beneficial role in thermoelectric generators, thermocouples, and temperature sensors, etc. Seebeck applications of polymer. Seebeck effect of conducting polymer make interest due to these following applications like thermocouples, thermoelectric generators, high frequency power sensors, security alarms, thermopiles, space probe, etc. Objective of my research: as the demand of alternative energy sources increasing day by day, so there is a need to make a device that convert the waste heat into electricity, and the thermoelectric devices are the best candidate to convert the waste heat into electricity. So objective of my research is to synthesize polyaniline manganese dioxide composite by polymerization process. Polyaniline manganese dioxide composites were reported in literature, but its extensive study were missing. So my aim is to analyze the temperature dependent DC conductivity and calculate the Seebeck coefficient and current density for Seebeck measurements. Synthesis of polyaniline. For synthesis of polyaniline, I take two separate beakers. In both beakers, I add 50 ml deionized water. Then in first beaker, I add 12.25 gram of APS, while in second beaker, I add 5 ml aniline, and I stir it for 30 minutes. After 30 minutes, I mix the solution and stir it for further half hour. Also, I add 5 ml HCl drop wise. Then I left the solution for polymerization for 24 hours. Then I filter the solution with deionized water to remove impurity, and finally I get polyaniline. Synthesis of polyaniline doped with HCl is similar with polyaniline, just instead of deionized water I used HCl in both of my beakers. Synthesis of polyaniline doped with HCl MnO2 composites. For synthesis of composite, I take two separate beakers. In first beaker I add 5 ml aniline, while in second beaker I add 12.25 gram of APS. Also I add 50 ml of HCl in both the beaker. Then I stir it for 30 minutes. After 30 minutes, I mix the solution and further stir it for 1 hour. Then I add 5% or 15% of MnO2 and further stir it for 1 hour. After 1 hour, I will add the 5 ml HCl drop wise to adjust the pH. Then I left the solution for polymerization for 24 hours. Then I filter the solution with deionized water. And finally, I got the polyaniline manganese dioxide composites doped with HCl. So result and discussion. XRD of polyaniline. As you can see that the XRD of polyaniline have two broader humps at the range of 19 to 27 degree. These two broader humps represent the amorphous nature of polyaniline. So polyaniline is amorphous in nature. XRD of polyaniline doped with HCl. X-ray diffraction pattern of polyaniline doped with HCl. Polyaniline doped with HCl have amorphous peak at 25.23 degree. It indicates the amorphous nature of polyaniline doped with HCl. Also, the hump of polyaniline is also present. XRD of pure MnO2. As you can see that XRD of pure MnO2 is well crystalline in nature. XRD result declares that MnO2 is well crystalline, and the highest intense peak is observed at the 2 theta 37.2 degree, and all the peaks of MnO2 were identified by using JCPDS card number 140644, and all the peaks represent the well crystalline nature of manganese dioxide. XRD of my composite sample: 5% MnO2 and 15% MnO2 composites. As you can see that all the characteristic peak of MnO2 presents in my composite sample. So there is a good interaction between polyaniline and MnO2 composites, and by using JCPDS card number 140644 all the peaks were identified. and no additional peaks were discovered in composite. Also, you can see that as the weight percent of MnO2 increases in the composite sample, the crystallinity of Pani will increase. The sharpness of peak will be increases. The peaks of MnO2 become more prominent. That confirms the formation of polyaniline manganese dioxide composite doped with HCl. IV characteristic curve of pure polyaniline and polyaniline doped with HCl. As you can see that here these are the graph for my pure sample and HCl doped sample. As the temperature increases, the slope of this curve will be increases. Also, in case of my composite sample, 5 weight percent or 15 weight percent MnO2 composite, as the temperature increases, the slope of this curve will be increases. So you can see that these curves have higher slope at 393 Kelvin. DC conductivity of polyaniline doped with HCl and polyaniline doped with HCl MnO2 composite. These are the characteristic curve of conductivity versus temperature at given range of temperature of my pure sample and my composite sample. You can see that as the temperature increases, the conductivity increases. Also, as the weight percent of MnO2 increases, the conductivity increases. The reason is that MnO2 is a semiconductor. As the temperature increases, the resistance will be decreased. So by conductivity formula, sigma is equal to L over Ra. If the value of resistance will be decreases, so conductivity will be increase. Also, by adding the more weight percent of MnO2, the carrier concentration enhanced, so the value of conductivity will be increases. So these are the table and the calculated values of my pure and the composite sample. You can see that at 313 Kelvin, the value of conductivity of my pure sample is 8.51 multiplied 10 to the power minus 7, but at 393 Kelvin its value become 2.25 multiplied 10 to the power minus 4. So the conductivity increases as the temperature increases. Also you can see that at 393 Kelvin its value of my composite sample become 9.03 multiplied 10 to the power minus 4. So you can see that as the weight percent of MnO2 increases, the conductivity will also increases. So activation energy of polyaniline doped with HCl and polyaniline with HCl MnO2 composite. By using Arrhenius exponential equation, sigma is equal to sigma naught e की power minus c over kt, where sigma is the DC conductivity, sigma naught is the pre-exponential factor, E is the activation energy, minimum energy required to initiate a chemical reaction, K is the Boltzmann constant whose value is 8.616 multiplied 10 to the power minus 5 electron volt per Kelvin, T is the absolute temperature. By taking ln on both sides, ln sigma is equal to ln sigma naught minus E over K multiplied 1 over T. So by comparing this equation with straight line formula, y is equal to mx plus c, I got the value of slope that equal to m is equal to minus E over K. So activation energy become minus slope multiplied by Boltzmann constant. So these are the ln sigma versus 1 over T linear fit that I calculate by origin pro 8 by using linear fit function. So these are the calculated slope of this graph and the Boltzmann constant value. So by multiply these values, I will calculate the activation energy, and you can see here the trend. As the weight percent of MnO2 increases, the activation energy will be decreases. So the less energy required to initiate a chemical reaction in case of composite sample. Seebeck coefficient of HCl doped polyaniline and HCl doped MnO2 composite. Here you can see that MnO2 is an n-type semiconductor. So in my composite sample, these values are in negative. So as the weight percent of MnO2 increases, also the temperature increases, the Seebeck coefficient will be increases. The reason is that Seebeck coefficient is directly proportional to the applied potential difference. As the potential difference increases, So the temperature increases, so the value of Seebeck coefficient will be increases. So these are the calculated values of my Seebeck coefficient of my pure sample and the composite sample. You can see that at 313 Kelvin, the value of my pure sample Seebeck coefficient is 0 millivolt per Kelvin. But at 373 Kelvin, I calculate the value of 32 millivolt per Kelvin, and in case of my composite sample, its value increases and reaches to 52 millivolt per Kelvin. Measurement of current density by Seebeck coefficient. The current density of HCl doped polyaniline and polyaniline MnO2 composite doped with HCl is calculated by the following relations, also called the microscopic form of Ohm law. J is equal to sigma. Mistake 2. Measurement of current density by Seebeck coefficient. The current density of HCl doped polyaniline and polyaniline HCl doped MnO2 composite calculated by using this relation known as a microscopic form of Ohm law. J is equal to sigma EMF minus delta V. J is equal to sigma EMF minus S delta T by using Seebeck coefficient formula. So as the temperature increases and the weight percent of MnO2 increases, the current density will be increased. As the carrier concentration increases, more covalent bonds will be broke, so the value of Seebeck coefficient will be increased. So these are the calculated value of current density. You can see that in case of pure sample at 373 Kelvin, the value of current density is 3.57 milliampere per centimeter square, but in case of composite sample, its value becomes 17.57 milliampere per centimeter square. Conclusion of my research work: the in situ molecular polymerization approach has been utilized to effectively synthesize polyaniline, HCl doped polyaniline and HCl doped polyaniline MnO2 composite. The structure of polyaniline doped with HCl and composite were confirmed by XRD. All the planes of manganese dioxide were reported in literature by using JCPDS card number 140644. As the weight percent of MnO2 increases in polyaniline, the crystallinity increases. The peaks of MnO2 becomes more prominent, and MnO2 increase by weight percent in Pani, which confirm the formation of Pani MnO2 composite doped with HCl. Temperature dependent DC conductivity 313 to 393 Kelvin was conducted by Keithley 2400 source meter and studied in detail, which was not reported in literature. The studied sample showed good conductivity at temperature of 393 Kelvin, and maximum conductivity is observed for HCl doped polyaniline 15 weight percent MnO2. Electrical properties were observed for polyaniline and HCl doped polyaniline composite shown in semiconducting behavior, in which conductivity increase and temperature efficiency of charge transport between the polymer chain and the dopant. The Seebeck coefficient of all sample linearly rise by increasing the temperature and by increasing the concentration of manganese dioxide and reaching the maximum value of 52 millivolt per Kelvin from 32 at 373 Kelvin. Also, the current density of all sample linearly rise by increasing the temperature and by increasing the concentration of manganese dioxide and reaching the maximum value of 17.57 milliampere per centimeter square from 3.572 at 73 Kelvin, which suggests that the synthesized material are the good candidate for thermoelectric devices like thermoelectric generator, thermopile, etc. So stay blessed. Allah Hafiz.